Hello, sir. Hello, sir. Can you hear me?
Sir?
Come on. So it says something. What is this?
Yes, sir. Sir, are you here, sir? Sir, Dr. Muthuswamy, sir. Hello.
You can see. You can.
Dr. Muthuswamy Nallal,
I
sir.
cannot listen any sounds.
Hello, sir. Dr. Muthuswamy Nallal, sir.
Sir, some other webcam, some other thing interrupting our இது.
புரியல.
யாரோ ஒருத்தர் ஜாயின் பண்ணிருக்காங்க. வேற ஏதோ வெப்காம் யூட்டிலிட்டி ஏதோ வேற ஏதோ புதுசா ஒன்னு ஜாயின் ஆயிருக்கு சார்.
Okay. Hello, sir.
வெப்காம். யாரும் தெரியல பாருங்க என்னன்னு தெரியல.
Hello, sir. This is Muthuswamy from South Korea. Can you hear me?
Yeah, yes, sir. Yes, sir.
Okay. Welcome you, sir. Welcome you, sir.
Thank you, sir.
Sorry,
Thank
some
you,
other. Okay, thank you. Welcome.
Thank
Okay,
you.
sir.
Thank you.
Actually, I have a little problem with my system. That's why.
Yes, sir. Yes, sir. Sir, I am Dr.
Okay.
Raja. I am Dr.
Oh.
Raja, senior of Dr. Anandavelu.
Oh, okay, sir. Nice to meet you, sir.
Yeah. I have done my PhD at Alapa University.
Oh, nice.
And,
Happy to hear, sir.
Yeah. Thank you so much. Thank you. And
The
madam,
session
introduce yourself.
starts at 5 o'clock. Please.
Madam, introduce yourself. Madam.
No, nothing, sir. No.
Okay, sir.
Dr. P. Suryakala, sir. Dr. P. Suryakala.
Oh,
Faculty,
okay, sir.
faculty in physics. She is my colleague.
Okay, sir. Nice to meet you, ma'am.
Okay, thank you, sir. Thank you.
Mr. Dhananjayan, sir. Dhananjayan, sir.
See you tomorrow. Bye. Sorry, sir. My junior sir left from lab.
Okay. Now you are in China, sir?
So now I'm in Korea, sir. Hanyang University.
But
Previously I was in China.
Oh, okay. Now you are in Korea.
Yeah, Korea, Hanyang University. I think you might know.
ஆனந்தவேலு இதை சென்ட் பண்ணியிருந்தான். அதுல வந்து காலேஜ் ஆஃப் பிசிக்ஸ் ஆப்டாலஜி இன்ஜினியரிங் சென்சாங் யூனிவர்சிட்டி சைனான்னு இருந்துச்சு. அதவே இன்விடேஷன்ல போட்டு விட்டேன். சாரி சார்.
இல்ல பரவாயில்ல சார். ஆக்சுவலி அது வந்து அண்ணங்களோட யூனிவர்சிட்டியில நான் பிரசன்ட் பண்ணல அனுப்பிச்சு செய்யுங்க சார்.
சரி
தான் நான் அதை கன்ஃபார்ம் பண்ணேன் சார். ஏன்னா ஏஎஃப்எம்ல அந்த இதெல்லாம் கொஞ்சம் பிஸியா இருந்தனால எனக்கு டைம் கிடைக்கலைங்க சார்.
ஓ சரி சார். ஏஎஃப்எம் ஹேண்ட்லிங் வந்து அந்த முக்கியமா அந்த மோடு வைக்கும் போது தான் ரொம்ப ஷார்ப்பா இருக்கும். அந்த நீடில் எல்லாம் உடஞ்சிரும். டைமண்ட் நீடில்.
ஆமா சார். அந்த ப்ரோப் வந்து மோஸ்ட்லி நம்ம பசங்க தான் ஹேண்டில் பண்ணிட்டு இருக்காங்க சார். அதனால
ஆமா. நாங்க ஒர்க் பண்ணும்போது ரெண்டு மூணா உடைச்சு விட்டேன். அது ரொம்ப கேர்ஃபுல்லா அது ஒண்ணு. ஆமா.
ஓகே சார்.
நீங்க கண்டக்ட் மோட்ல நான் கண்டக்ட் மோட்ல பண்றீங்களா சார்?
சோ இப்போ வந்து கண்டக்ட் மோட்ல பண்ணிட்டு இருக்கோம் சார்.
கண்டக்ட் மோட். சரி. ஃபில்ம் தான் பண்றீங்க சார்?
இல்ல, ஃபுல் அண்ட் ஃபுல் என்னோட ஒர்க் வந்து ஸ்டடிஸ். இது வந்து ஒரு நியூக்ளியேஷன் growthக்காக கொஞ்சம் ஒரு மெக்கானிசம் ஐடென்டிஃபை பண்றதுக்காக ஒரு சாம்பிள் ப்ரூவ் பண்ணி கொடுத்துருக்கேன் சார்.
ஓகே சார்.
பிசிக்ஸ் டிபார்ட்மெண்ட்ல அவங்க கண்டக்ட் எடுத்துட்டு இருக்காங்க சார். கொலாபரேட்டிவ் ஒர்க் மட்டும் பண்ணிட்டு இருக்கோம் சார்.
ஓகே. இப்போ உங்க இதுல ஏதாவது பிஹெச்டி அல்லது மாஸ்டர் ஸ்டூடெண்ட்ஷிப் ஏதாவது வந்தா சொல்லுங்க சார்.
கண்டிப்பாங்க சார்.
சார், டாக்டர் கனக சபாபதி from chemistry department.
Hello sir, good evening sir.
Good evening sir, nice to meet you sir.
Right sir. We are so pleased to hear your talk sir. Very interesting topic.
And he has done his PhD at Central Electrochemical Research Institute, sir.
Secret. Oh really? So I also did my project in Central Electrochemical, sir.
Okay sir. Super sir.
In electronics department, and then I worked in electroplating department, sir.
Oh, under whom sir? Electroplating.
Under Dr. Mohan.
Mohan sir. Okay sir. Sir is known to me, well known to me sir. Great sir. Great thing sir.
After that I moved to Korea for my PhD.
Okay sir. Very good sir.
It's long time.
Chemistry.
Okay sir. Great sir. I'm glad to meet you sir. Okay sir.
Thank you.
He's your mother department. Chemistry.
Oh yeah.
நீங்க ஆனந்தவேலு ஜூனியர் தானே?
ஆமாங்க சார். ஆனந்தவேலுனே நான் எம்ஃபில் முடிக்க போறேன். எம்ஃபில் ஜாயின் பண்ணல அண்ணன் PhD முடிச்சாங்க சார்.
முடிச்சிட்டான். சரி.
ஆமாங்க சார். 2000
தனசேகர் கேள்விப்பட்டிருப்பீங்கல்ல? தனசேகர்
அதான் நான் பாத்துருக்கேன் சார். நேரா மீட் பண்ணிருக்கேன் சார்.
ஆமா நாங்கெல்லாம் அங்க. சரி. வந்துருங்க தலைவா. ஆமா, நாங்கெல்லாம் என்னுடைய ஜூனியர்ஸ் தான் அவங்க எல்லாருமே.
சரிங்க சார்.
கோபால்ராம, தனசேகர், இவன் ஆனந்தவேலு எல்லாரும்.
அப்புறம் நீங்க ப்ரொஃபசர் கோபாலன் சார் உங்களுக்கு தெரியுமில்லங்க சார்?
நான் வந்து எம்எஸ்சி வந்து 2002ல பண்ணேன் தம்பி. அப்ப பண்ணும்போது அப்ப கோபாலன் சார் வந்து கொரியா போனாரு. அப்ப
நான்
தெரியும்,
கோபாலன்
கோபாலன்
சார்
சார் தெரியும்.
எனக்கு கோபாலன் சார் கோ-கைடுங்க சார்.
ஓ அப்படியா? சவுத் கொரியாலயா?
ஆமாங்க சார்.
சரி சரி. அவருடைய ஸ்டூடெண்ட்ஸ் ஜெர்மன் போனான். பேர் என்ன அவருடைய ஃபர்ஸ்ட் ஸ்டூடெண்ட்?
இவர் நம்ம கோமதி அக்கா, அப்புறம் அதுக்கப்புறம்
கோமதி.
ஆமாங்க சார்.
ஆமா கோமதி ஃபர்ஸ்ட் ஸ்டூடெண்ட். அவன்தான். அவங்க எல்லாருமே அப்போ கெமிஸ்ட்ரி டிபார்ட்மெண்ட் தான் நிறைய பேர் பண்ணிக்கிட்டு இருந்தாங்க.
ஆமாங்க சார். சேம் லேப் என்னோட ப்ரொஃபசர் கீழ தான் வந்துட்டு இருந்தாங்க சார். ப்ரொஃபசர்
கோபாலன் வந்து அவர்தான் லீடிங், நிறைய பேப்பர் பப்ளிஷ் பண்ணாரு. அதுக்கப்புறம் அங்க இருந்து போனவர் அதுக்கப்புறம் அலோபா யூனிவர்சிட்டி வரவே இல்லை. அவருக்கு அவ்வளவு சேலரி நினைக்கிறேன் இங்க கொரியால.
ஆமா சார், இங்கேயே செட்டில் ஆயிட்டாங்க சார். இப்போ சார் ஆஸ்திரேலியா போயிட்டு திருப்பி கொரியா வந்திருக்காரு. இப்போ இந்தியால தான் இருக்காருங்க சார் சார்.
ஓ அப்படியா? எங்க இருக்காரு? ரெஸ்ட்ல இல்ல திரும்ப உங்க வர்றது மாதிரி ஐடியாவா?
ரெஸ்ட்ல இருக்கணும்னு கேள்விப்பட்டேன் சார். நான் இன்னும் சாரை மீட் பண்ணலைங்க சார். சோ அங்க திருநெல்வேலியில இருக்குன்னு கேள்விப்பட்டேன் சார்.
உங்க ஹெச்ஓடி அப்போ வாசவன் சார் இருந்தாரு அப்ப.
ஆமாங்க சார்.
கேள்விப்பட்டிருப்பீங்க. அவரு வந்து கலசலிங்கத்துல நான் ஒர்க் பண்ணும்போது அங்க ரெஜிஸ்ட்ராரா இருந்தாரு. அவரும் கொரியா போனாரு. கோபாலன் சார் கூப்பிட்டாருன்னு கொரியா போனாரு.
பக்கத்துல ஜாயின் பண்ணியிருந்தாங்க சார்.
ஆமா. சி ராமலிங்கம் கேள்விப்பட்டிருப்பியா? ராமலிங்கம்.
ஆமாங்க சார். பிசிக்ஸ் டிபார்ட்மெண்ட் இதுல சென்னை பேஸ்ட் நினைக்கிறேன் சார். சாரு
இல்ல கலசலிங்கம் யூனிவர்சிட்டில இருக்காப்ல. இப்ப டீனா இருக்காப்ல.
சரிங்க சார்.
நான் ஒர்க் பண்ணா அவரு அங்க கொரியால 8 வருஷம் இருந்தாரு அவரு.
சரிங்க.
அவரெல்லாம் பிளான் நான் நிறைய பேரை கூப்பிடணும் பிளானு. இந்த செமஸ்டருக்கு நாங்க அந்த ஆக்டிவிட்டி பண்றதுனால டக்குன்னு பண்ண வேண்டியது. ஏன்னா அடுத்த வாரம் ஒரு FDP இருக்கு.
சரிங்க சார். ஆக்சுவலா எனக்கு பிரசன்ட் நான் என்ன பண்றது தெரியல.
இல்ல இஸ்ரேல்காரன் இது புரியல
சார். கேக்குதா சார்?
ஓகே தம்பி, we are going to start a program. Okay.
Okay sir. Okay sir.
Okay.
I think I did not link my PPT, sir. Is it possible to change presentation file, sir?
Sir.
Raja sir.
Good evening, sir. Good evening to one and all present here. First of all, I welcome all the participants and today's chief guest. Actually, there is a slight change in the schedule. Today's guest speaker is Dr. Muthuswamy Nallal, and he is going to give a lecture on current scenario in advanced materials research and nanotechnology. Today's section will be a useful session for all of us for the Department of Physics. And on behalf of Rajapalayam Rogers College and the Department of Physics, once again I welcome you all and also the speaker. I invite Dr. M. Raja to give the introduction about today's speaker.
Thank you,
Raja,
madam. Thank you, madam. So I'm pretty happy to introduce our today's chief guest, Dr. Muthuswamy Nallal. He has done his MSc in Vivekananda College, and he has done his PhD, MPhil at Alabama University from 2012 to 2013. And 2012 to 13, he was a project student at Central Electrochemical Research Institute. Based on his merits, he got a PhD funded opportunity in Gyeongpuk National University, South Korea. He has completed PhD at 2017, and after that he has joined as a postdoctoral researcher the same university from 2017 March to August, and then he joined as a postdoctoral research postdoctor in the Department of Chemistry, Busan National University, Busan, from 2017 to 2019 as a postdoctoral researcher. Presently, Then 19 to 22, he has done his postdoc research in the College of Physics and Optoelectronic Engineering, Shenzhen University, and in China. Then at present, he is doing postdoc at South Korea. So I'm pretty happy, sir. Thank you. Sir, welcome, sir. Welcome, sir.
Thank you, sir. Thank you for your kind introduction, sir.
Sir, you can continue, sir.
Thank you, sir. Thank you, sir. Good evening, everyone. This is Muthuchami from Korea. So actually, I really happy to meet you all. Actually, most of all my seniors. Like I'm very young to share my research with you all. So it's really happy. So I always think that like sharing research with like people, it's make more safe of my knowledge to achieve my like goal. So here I eagerly wait to share my like past and future research. So today my research topic is related to like biosensors. Like most of us, like I heard that like the conducting department is physics. So maybe you hope understand about my topic. So my title of the presentation is like advanced nano materials and its biosensor applications. So as we know that like recent years, nano materials plays plenty of role in the various sectors, like even like from the morning to midnight. So what are the things we do? So it's always depend on the material. Even that material has a lot of combined with the nanotechnology, so it gives like more advantages. So for that reason, like most of the researchers and most of the like young people, they are impressed with the nanotechnology.
Yes, sir.
So can you hear me?
Can you able to move the slide, sir? Move your slide.
Oh, really? You cannot see my slides,
sir?
So just a minute, sir. So wait, sir. I will share my slides. Present now, then. So
sir?
Can you see my slides, sir?
No, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay, okay, sir.
Now, okay, sir. Now, okay, sir.
So, okay, sir. Thank you, sir. So if anything happen like internet, just let me know, sir. Because while presenting, I cannot see the commands. So
okay, sir. Okay.
Just let me know, sir. So my the ongoing topic is like advanced nanotechnology and its application for biosensors. Mostly we know that nanomaterials. So here we need some functional nanomaterials for the biosensor applications. So we know that nanomaterials, it's always the scale. Anyone like dimension, it should be like length or height or width. It should be under nanoscale. So also when we change the dimension size to nanoscale, obviously the property of raw material it change. So we need some functional groups to functional like additional functional materials or groups to enhance the our applications property. So we used to go for the functional nanomaterials. Here functional nanomaterial is an organized molecular entry with capacity for probing as a specific function under the specific set of the work environment. So there are plenty of like methods are available to synthesize the nanomaterials. So most of like widely available methods are like hydrothermal methods and ultra deposition methods and co-precipitation and micro deposition or micro oxidation redox methods and like laser ablation in the liquid like LAL and then spray pyrolysis and high temperature shocking methods. So here you can see that various morphologies and various properties of the synthesis and functional nanomaterials. Like most of materials, it's nanoparticles and amorphous and highly entropy, like a single atom nanomaterials and coastal nanomaterials and compound and nanomaterial compounds and stocking fluids and graphenes, like 2D materials and 3D materials and like 1D materials and multi-dimensional materials, ceramics materials and salts like combined multi-nano atoms and carbon-based nanomaterials like that. Here, functional nanomaterials we use like mostly in our group we use like functionalized conducting polymers with nanomaterials. So here we used to synthesis like 4 type of materials. One is like a substituted derived like conducting polymers based nanomaterials, and biofunctionalized conducting polymer based nanomaterials. Then nanostructured functional conducting polymers with nanomaterials, and multi-component conducting polymer based nanomaterials. Here we can see the carbon nanostructure, and like example like CNT, carbon nanotubes, graphenes, and other like dimensional carbon based nanostructures, plus like a metal or metal oxide components and nanostructures like materials for make a like good biosensor probes. So these are the methods like materials where we here we prepared in our groups. So nanosponge we prepared from the polymers with DAO to graphene nanowires, and coastal nano rods with like polymerization after the nano rod from the electrospinning method. Then nano beads, it's like multi-component nano feeds. Then like coastal structures and the 3D nano stacks. Then nanoflower materials from the diamond based materials, and 2D nano seeds. After the like hydrothermal method, we prepare the 2D nano seeds from the like bismuth haloxide with graphene materials. Then like nanoparticles, like coastal nanoparticles, then nanowires and coastal nanowires, then hydrogels, then nanocomposites and
Sir,
nanohybrids.
sorry for the disturbance. Sir, can you please go for the presentation mode? We could not see clearly the slides.
Okay, ma'am.
Okay, thank you, sir.
Can you see now?
Yeah, yes, sir.
Okay, ma'am. Thank you, ma'am.
Yeah, thank you, sir.
So these are the materials where, like here we prepared, like we utilize these materials for the biosensor application, also some energy-based applications. So like now the two sectors are very, very important. One is like bio-based research, another one is like energy-based research. So bio-based research, it's mainly focused on like nowadays, like after the corona, so world are very curiosity about the biology systems. So most of the researchers, they're moving towards the biology-based research. At the same time, we need like sustainable energy to sustain life. So for that, like most of the groups, they're moving towards the energy also. So here we have like 3 groups. One group, they always focus for environmental studies. Then another group focusing biosensor groups. Then another group, they focus energy. So my role, like I have to combine both biology, like biosensors and energy. So due to the electrochemical experience, I used to combine these both. So biosensor, like biosensor, it's not only play a role in the biological system, it's also play in the like monitoring salts, like solid quality, also the food quality and pathogen and drug delivery, also the detection of like toxicity molecules in the chemicals, and water monitoring and disease detections, also the environmental monitoring. So these are the main sectors where the biosensor play a key role. So here I use like upcoming 3 works. It's always a focus on the one is like nitrate ion detection, so which is very important in for the human. So once the nitrate ion is increasing in our body, always it makes like blue eye disease. So which one happened in USA like in 2020, 2000 like 20 centuries. It makes like a lot of problem for the like people in the USA, so not the USA. Also, after that, another 2 works, it's based on the glucose sensor, also that HPONAC sensor, then non-intermediate glucose sensors. So here we use like 2 kind of techniques for the biosensor application. One is like photoelectrochemical, another one is electrochemical techniques. So electrochemical techniques, we know that we need like current, with the potential and current play a main role. And photoelectrochemistry, it's nothing but additionally we are applying the current, light source to enhance the sensing the response. So we know that like in the electrochemistry, we used to get current as a result, like current as a result. Here when we apply the photo, the current and the enhancing current we can monitor. So the photo enhanced current, it gives the like a proper parameter to optimize the sense the parameter sense the sunlight. So for that reason we use the photo electrochemistry first. So after that, some cases like when we apply photo on the biomolecules, sometimes like photosensitive biomolecules, it's make like decompose or make some side effects. So for that reason, we stop until the electrochemistry. So here you can see that like electrochemical techniques, we need only that unlight and biosensing element. It should be like electroconducting material. Also, it's bio-friendly material. Then transmitter, which is like we need to collect the response. Then signal processing. So from the signal processing, we can get response. In the photoelectrochemistry, additionally, we are applying the light source, which makes like monochromators. So sometimes we can apply some white light source also. From the workstation and signal processing, signal acquisition process, we can get that signals. So here you can see substrate, like substrate should be like conducting material, also the photoactive material, and probes. The probes should be find with like analyte, then target molecules. So these are the main things in the photoelectrochemical biosensors. So here the selection beyond the functional nanomaterials for the photo and photoelectrochemical applications. So as we know that like that electrode material should be the photoactive, also should be the electroconducting material. So for the reason we can take like semiconducting materials. So semiconducting material should be it's always a photoactive materials. So also it has the conductive property. So here the main requirements it's like superior properties in the electrical and optical and some cases mechanical because of separation of applications. Then biological and chemical and catalytic systems should be adapt with the system, and unique structural properties also, because structural based sensors are available. So nowadays like wearable sensors are almost based on the structural based the sensors. So the advantage of these things like easily availability and tunable structure and surface composition and good catalytic activity and fast reaction rate and low cost and highly stable. Then here we use like a carbon supports, like mostly of the material, like when we go for the novel metal based or like highly cost materials, we cannot adapt with the price. Also we cannot adapt with like economically like a cost wise. So we need low cost material which should be more conducting material. So we use like carbon supports here, large pore volume, because carbon materials always has large pore volume, then ideal force size distribution, and it always shows like high surface area and high electrical conductivity and good charge carrying. Due to these properties, we have to select the good candidate for the like photoelectrochemical sensors and another few phase sensors. So first one is like in this work, like a novel photoelectrochemical biosensor platform is discovered by the modifying the graphene with the electroconducting polymer narrative like nanosponge and TAO to nanowire. So first TAO to nanowire prepared from the electrospinning method. After that, we modified with polymerization to make a polymer nanosponge. So in the inclusion of graphene and TAO to nanowire in the electropolymer nanosponge along with the immobilized cytochrome C. So prove the basis for the construction of highly sensitive and selective photoelectrochemical biosensor for the nitrate ion. So these are the main role. So under the light, you can see the. So when we pass the light, our main objective material exhibits like improve the performance with very low bias potentials. It shows like around -1 volt with respect to AGSL electrode. So once we prepare the material, so first step we have to modify with TAO to graphene nanowire. Then after then polymerization. So after the polymerization, we functionalize with the cytochrome C. Then after the cytochrome functionalized with the cytochromacy, we utilize the final material for the nitrate ion sensing with the photoelectrochemical technique. So this is the schematic presentation of this work. So here some basic morphology studies. You can see that non-sponge like structure of prepared TiO2 graphene nanowire like electroconducting polymer nanosponge. So we have to confirm whether like only TiO2 graphene nanowire shows like sponge like structure or not. So we prepared without polymerization also. You can see it shows only the nanowire strafe. So the nano sponge, it shows like combined with the graphene and TiO2 and polymer safe. You can see the amorphous surfaces are the polymers, and the exact that graphene shows like its fringes, and TiO2 also shows the same things. So you can see without like graphene, the shape of the nano sponge, it's like kind of amorphous and unsafe. It's not like rectangular shape. So that's why like a graphene plays a main role to make a safe control. And here you can see only the pristine polymer nanosponge, it didn't show any porosities or any like morphology control structures. So for that reason, we confirmed that graphene play a main role to the rectangular plug like nanosponge formation. Also, that polymers plays play a role for the amorphous structure, and TiO2 graphene play a main role for the like porous and rectangular shape structure. And when we go to the application part, TiO2 it's one of the like semiconductor, and graphene as a conducting material, and polymer with the functionalized polymer, it's play a main role to finding the cytochrome. Then cytochrome it's play as a enzyme, it's play a role to like react with the nitrate ion. In here you can see we optimized the pH conditions and the loading of the catalyst. Also we confirmed that nitrate ion sensing potential through the linear strip hold down technique. So here you can see like without light and with light, obviously that photo enhanced current, it's noted around like around 700 millivolt. So it shows that nitrate ion sensing, it's happened around like 700 millivolt. But thing is like when it's coupled with the bias potential, we can see around 0.1 volt. It's enhanced the current. So we have two potential. One is like oxidation potential, also the enhanced potential. Might be that bias potential, it's helpful for the first absorb the nitrate ion, then oxidize at 0.7 volt. So here you can see the schematic expression of the sensor work. So when we place in our material in the dark condition, there is no enhanced current. So when we apply the photo, we got the photo current response. So that means light play a main role to enhance the photo current. So when we add the different concentrations of nitrate ion, so in the photo like chronoamplimetry technique with the photo adjustment of photo, we got that photo current with respect to the concentration of nitrate ion. So we got that maximum the concentration of nitrate ion around like 9 millimole. So also the linearity and rapid sensing time, it's around like 5 seconds. So it shows like good sensitivity, also it's excellent selectivity, because you can see the sorry, I didn't present that data. So the selectivity, it didn't show any like interpret response towards the selectivity. Also it shows like wide linear range. You can see from 0.5 to 9 millimole. 9 millimole. That means it shows like wide linearity. So also when we go to the load reduction limit, it's very, very important. So when we go to the load reduction limit, shows like really good load reduction amount. It's around 0.5 micromole. the stability and applicability for the detection of nitrate ion in the real sample also we perform. So it shows like that our like fabricated biosensor, it's really suitable for the nitrate ion sensor with adjustment of photocurrents. So we enhanced that concept of the designed like photovoltaic biosensor platform with a composite material containing graphene and photoactive material with and a polymer and extendable towards the fabrication of biosensor for other analytes through the prestige choice of the component with an enzyme. So these are enzyme-based biosensors. So other than again we move to the like non-enzymatic biosensors. So why we should move to the non-enzymatic biosensor? Because some enzymes it's not stable always. So we have to find out the non-enzymatic biosensors. So here we use like two techniques. One technique like photoelectronic biosensor for glucose with non-enzymatic technique. Another one is like electrochemical biosensor for the like HPN biosensing. Almost we know that like when we go to clinic, first we used to check the glucose level of our blood. So the glucose level of blood, it's always depend upon the what kind of food we took. Like we had night or like within 4 hours. So here that's why like most of clinic people they used to ask to take glucose level monitor like before fasting and after fasting. So this is the main role. So but it's always depend on food, right? So some doctors they used to just to take HbA1c because the HbA1c its detection value is always shows like past 5 to 6 month glucose level of average glucose level of our blood. So that's why we selected both glucose molecules and HbA1c in the real samples. In the sensor probe fabrication, first we prepare TiO2 nanowire with the electrospinning method. Then we polymerized with 3-aminopenyl boronic acid. Then we like cell formation with cold nanoparticle. So here gold nanoparticle also play a main role to enhance the current. As we know that cold nanoparticles have like some light responses. So here the morphological presentation you can see. So in TEM image you can clearly see that like in middle like core as a TiO2 graphene wire, then cell polymer and the black dots are gold nanoparticles. So with the more resolution images we can confirm that like gold and TiO2 and graphene structures. So without polymer like cell formation, you can see that only like a few dots of polymers like TiO2 available. So it didn't show coastal nanostructure. That means like polymer polymer and cold cell formation, it's formed very perfectly. So these are the some basic mechanism for the photoelectrochemical glucose biosensor. You can see that like there is no enzymes here used. Like mostly in nitrate sensor we use cytochrome C, right? So mostly for glucose sensor, the people they used to use glucose oxidase for as a binder for the glucose molecule. So here we use like boronic acid, the 3-aminopenyl boronic acid, right? So the boron groups, like boronic acid groups, like boron and OH group, that itself it's play like binder of glucose molecules. So it's really like a dual functional. So it can be enhance the conductivity of the current. Also, it can be find the glucose molecules from the analyte. So boronic OH group, it's really helpful to the bifunctional role in this work. So you can see that like we prepare like 3 kind of material. One is like without polymer, another one is like without graphene, another one is like only gold nanocomposite without TiO2. So you can see like without TiO2 in C, there is little response like photo response. When you include with TiO2 nanowire without graphene, there are also some enhanced current due to the semiconducting property of the TiO2. When we include the graphene, the photocurrent increase. We know that I already told that the role of carbon in the like in photoelectronic biosensor, the carbon plays a main role to enhance the conductivity. So here, due to the high conducting nature, so we got that high photocurrent response. So the next one, so the linear range. So linear range here we got from 0.5 to 28 millimole. So you can see that when we add the glucose molecule, obviously the photo response current also it's increasing step by step. Then it shows like spontaneous response, like within 5 seconds we got the response. So that means it's spontaneous response. Just you need to drop your sample on the electrode surface. When we apply the light, obviously we got that response. So it's spontaneous response. When we go to the without like graphene, so you can see that linear range it's decreased. So due to the conductivity, also that graphene here, the graphene play a role to enhance the sensitivity range. And the LOD, like limit of detection also it shows like really good to the biological detections. So it shows around 0.11 millivolt. Then sensitivity its main role for the sensor. So here sensitivity shows like 549 milliamp per millimole per centimeter square. And another one is like here we use like for electrochemical technique to detect the HCP and AC sensor. I already told you that like some biomolecules it's like easily affect with light. So that case like here we use like HCP on AC molecule as a analyte. So when we apply light, so here the ion in the HCP and AC it makes the photo redox reaction. So we cannot use photo electrochemical technique for the HCP detection. So we selected only electrochemical technique. So here H2O2 as an intermediator. So when we reduce the H2O2, it bind with the Kim group in the HbA1c. So when we reduce the H2O2, the amount of H2O2 it's always directly proportional to the amount of the HbA1c in the biosensor. So here indirectly we confirm that our linear range of the HbA1c sensor it's around from 0 to 10%. So mostly in our human blood, it shows around 6%. So this bioproof we can use for the real sample analysis. So we utilized as a real sample probe. Then we published this journal, this work in ACS Applied Material Interferences. So the final work is like we fabricated non-instrumented glucose sensor based on the multi-component nano bead. So these are the like multi-component molecules which we prepared from the like graphene polymerized with the aniline and anthralinic acid. These are the first stage. Then we functionate with like a branched copper nanoparticles to enhance the conductivity. This is the main roles. This is a complex, one of the complex nano bead. So to confirm the biosensing probe, so first we performed in CV. You can see that. So when we increase the concentration of the glucose, always we got the oxidation of the glucose at 0.4 volt. So to confirm exactly the sensing the potential, we performed the DPV. So you can see that when we increase the concentration from concentration of glucose from 0.5 millivolt to 50 millivolt, so it increased on around like 28 milliamp the current. So also that potential is shifting towards the positive region. So it makes sense for the real application. So in this work we can utilize for the the company like kind of like industrial sensors, but in the real human serum sensor we cannot, because of when we increase the concentration, the potential is shifting towards the positive side. So when we go for the real glucometer, so we cannot fix the potential. So for that reason, this material we used in the glucose monitoring for the alcohol factories. So linear range from the 0.5 to 15 millivolt. Also, it shows like good response from the other interference molecules like lactose and dextrin and fructose and isoprotic acids and then acetaminophenes. So also it shows like when we compare with the two methods, one is like our developed sensor with commercially available glucose sensor. It shows really like recovery percentage around like from 99 to 100%. So we use this one for the real application. Still, like Korean companies, they are developing for the real application sensors. So just I move to the conclusion part. So in the first work we prepared like electroconducting polymer nanosponge coated with the diode graphene nanowires and like electropolymer nanosponge. Then we used for the we functioned with the cytochrome C. Then we used for the nitrate ion sensor. Then the final, so the second work we used like we prepared the same material. Then we utilized for the two molecule sensors. One is like glucose sensor with photoelectrochemical biosensor. Then HEP1AC with the electrochemical biosensor with the dual. That's why like the diode graphene nanowire with the like 3-amino boronic acid functional with the golden nanoparticles. So it's like dual functionality. Then we use the final one is like we use like efficient sensing material having with metal components like graphene, then carboxylated polyethylene, then ferrocene, then copper nanoparticles were adequately nanostructures as porous interconnected beads. So the porous interconnected beads play a role to the find glucose molecules. It enhances the photocurrent. They also this like non-insensitive glucose sensor exhibit excellent analytical performance such as like wide detection range and low detection limit, also the high sensitivity and selectivity. So in addition that the proposed non-insensitive glucose sensor showed the good accuracy for the serum samples, but when we move to the serum samples, it shows a potential shifting rate. So we stopped then in for real biological molecular detection. Also, it's providing the potential feasibility for use the clinical analysis. So apart from the glucose sensing, most of the three methods proposed for the fabrication of like multi-component nanofluids can be expected to achieve the high performance for other electrochemical devices for using other set of the components. So this is my research profile. So here, like the first three references is related to the today presentation. So apart from the sensor, I already told that our group doing some further other researches for the batteries, energy and sensor and environmental studies, right? So here batteries also battery studies and the electrocatalytic studies also we are doing here. Then sensor and solar cell application and drug delivery like drug loading and releasing analysis also we are performing, and high level separation. So for all these studies we utilize the nanomaterials. So it's time to thank my teachers from the Yadava College and Vivekananda College and Central Electrochemical Research Center, then Alagappa University and Kembuk National University, Busan National University. Then I really thank to my senior, like super senior, Dr. M. Raja, so assistant professor of in the Department of Physics, Rajapalayam Rajus College. Also, I thank every organizing committee. I thank you everyone. Hello, sir. Hello, sir.
Sir,
Thank you, sir.
Sir, excellent, sir.
Thank you, sir.
Excellent presentation.
Thank you, sir. Thank you, sir.
Dear participants, the last relative got accident, so immediately we had to change the chief guest. So thank you, Thambi. Thank you. Lastly, you have accepted to give a lecture. Thank you so much.
It's my pleasure, sir.
Thank you. Thank you.
So if you need like any clarification, just you can contact through the email, sir.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. Thank you. Thank you.
Thank you, everyone.
Mrs. Jayalakshmi.
Yes, sir.
You have to give a lot of things today.
Oh, okay, sir. Good evening
because
to all.
chief guest is going to operate AFM. He is in the very busy schedule. So, dear participants, please forgive us today only. Thank you. Thank you.
Sure, sir.
So no issues at all. Can you send the email because I have some more doubt. I just contact to him direct.
Yeah, sure. I'm sending the email, sir.
Okay. Thank you very much.
Jayalakshmi.
Oh, okay, sir. Good evening to all. On behalf of Department of Physics, Rajabalayam Rajus College, it's my pleasure to deliver the vote of thanks. At first, I would like to thank our chief guest, Dr. Muthuswami Nallar, who spared his busy schedule to grace this session. Your session is very helpful for young researchers like me. Thank you, sir. Then I would like to thank our management, principal, vice principal, and HOD for their uncentered support. Then I would like to thank all the participants from various colleges, university. Finally, I thank my staff members for the relentless support and my friends for your cooperation making this occasion a resounding success. Thank you all. Thank you, sir.
Thank you, star. Thank you, Jayalakshmi. Thank you, audience. Thank you. Tomorrow we will meet at sharply 4:50 p.m. Okay. Thank you.
Thank you, everyone. Bye. Good night.
Thank you, sir.